Okay, let me take roll. Okay, answer to your names, please. Aleo Legaris Adrian.
Here.
Aleo Legaris Justin.
Here.
Bingy.
Here.
Francois. Let me see, is Francois here? But he's here. Folks.
Here.
Himes. Oh, Himes is here. Hodges. Let's see Hodges. Leave it. Lee is here. Malmberg. Don't see Malmberg. Martin.
Here.
Medina. Medina is here. Moreno is here. Perouche is here. Sammons. Don't see Sammons. Wheeler. Yes, Wheeler is here. White. Don't see White. And Zaragoza is here. All right, so last time we were here before your test, we did a couple of examples involving thermochemistry. Okay, so it is not that one. I'm sorry, I think before that. Back up a bit. Okay, yeah, so we did, I think we did both of them, if I'm not mistaken. All right. So okay, so let me talk about a special type of calorimetry known as bomb calorimetry, where this is used to determine the enthalpy change of the combustion of organic compounds. All right. So the design is a bit different from the calorimeter that we discussed before, because you have to do some burning. You cannot do the burning inside a coffee cup calorimeter. So this is basically the setup of that particular type of apparatus. Basically, you have this receptacle right here. This is where your organic material will be. That is encased in what is called a steel bomb. You have two electrical leads, which leads to the electric circuit outside, which basically allows for the ignition and burning of your organic material right here. What happens is that when this is burnt, the heat will pass through the walls of the bomb and enter the water here. And basically you can measure the temperature difference between the initial temperature of the water before the reaction and the maximum temperature achieved by the water upon the combustion of the material here. This is just basically a little kind of a fan that is used to make sure that the water is, or I should say, make sure that the heat is distributed evenly through the water. And that's basically it. Of course, there's some calculations you'd have to do in order to determine ultimately what the enthalpy change would be. All right. Key thing you need to remember about this particular setup is that this reaction is done in the constant volume situation. So therefore, the equation which relates the heat of the reaction to the heat change of the calculator is this equation right here, and that will be equal to delta U, which is the change in internal energy of the system. All right. And the point being made here is that even though delta U is different from delta H, in many cases, delta U can be used as a good approximation of change in enthalpy. All right. And that's all we're going to talk about with respect to bomb calorimetry. All right. Okay, so let's talk about a very important law, Hess's law of heat, of constant heat summation. All right. Very important law, especially when it comes to solving certain problems. Now, there are some reactions that, for whatever reason, usually it's kind of like logistic reasons or other reasons, that you simply cannot carry out in order to measure the enthalpy change, right? A good example of this is the reaction between carbon and oxygen to form carbon monoxide. Now, the reason why there's difficulty associated with doing this reaction is that the carbon monoxide itself can react or will react actually with oxygen atoms or oxygen molecules to form carbon dioxide, right? So as a result of that, it's very difficult to basically start off with carbon, react with oxygen, and you just basically stop here because this can react further with more oxygen to form carbon dioxide, right? So this begs the question, then let's say you're given the task of determining the enthalpy change of this reaction, then how can you determine it? Well, that is where Hess's law comes in. Key thing you need to remember is that enthalpy, like other state functions, only matter, or the change in the state function, in the case of enthalpy, is based on the initial and final states, and not the number of steps that you take going from the initial to the final step, all right, or stage. So this is Hess's law right here. It says if an equation can be expressed as a sum of two or more other equations, the enthalpy change for the desired equation is the sum of the enthalpy changes of the other equations, right? Now, let me explain this using a hypothetical example. Let me this up. Okay, so let's say you have a reaction that can go directly from A to C. Purely hypothetical. So you're going from A to C, right? And let's say the enthalpy change of this reaction is delta H3. All right, and let's say you can go from A to an intermediate B, and then from B to C, right? So let's say the enthalpy change going from A to B is delta H1, and let's say the enthalpy change going from B to C is delta H2, right? So what Hess's law is saying is that it doesn't matter if you go directly from A to C or from A through B to C. The enthalpy change overall is going to be the same. So the consequence of that is, in this particular hypothetical example, is that delta H3 would be equal to delta H1 plus delta H2. All right? So that's basically what Hess's law is saying. What it's saying is that it doesn't matter how you get from A to C, it doesn't matter how many steps, the total enthalpy change going from A to C would be the same, right? It doesn't matter if it's one step or more than one step, right? Another way of representing this is that you can write down A going to B, and the enthalpy change of that would be delta H1, and then B going to C, and the enthalpy change of that would be delta H2. So if you were to add these two, remember, whenever you add equations, you cancel items on identical items on either side. So you're going to end up with A going to C. Then this is delta H3, which would be the sum of these two, which would be equal to delta H1 plus delta H2, right? So this is just an alternative way of showing you how Hess's law works, right? And what you're going to see is that in the case of more complex examples, this way would be better than using the previous method shown, all right? So that's basically what Hess's law is all about. So going back to the carbon reacting with oxygen example, right? So this diagram here shows you, firstly, you start off with carbon reacting with oxygen, but going from here to here, the carbon here will be reacting with a half mole of oxygen, right, to form carbon monoxide, right? So that one is very difficult to measure experimentally, right? However, we know that going from carbon monoxide to carbon dioxide by the addition of half mole of oxygen, you're going to end up with CO2, and we know the value of delta H for that reaction. We also know that going directly from carbon to carbon dioxide, the delta H value is this right here. So basically, based on Hess's law says that it doesn't matter how many steps it takes to go from here to here. That means that the enthalpy change here will be equal to the sum of delta HA plus delta HB, right? And therefore, to find delta HA, let me do it here. Delta HA will be equal to delta HC minus delta HB. All right. So delta HC is minus 393.5 kilojoules minus 28, I'm sorry, 283.0 kilojoules. And whatever that gives, that would be the answer, right? So that's basically how Hess's law works. In fact, let me show you the other way, using the idea that I showed you earlier. Let me take this out and take that out. So I'm going to start off with carbon solid plus half O2. I'm sorry. I'm going to start off with carbon monoxide gas plus half O2 gas to give you CO2 gas, right? And I'm going to write down delta H for that, but before we do that, I'm going to also write down that C solid plus O2 gas to give CO2 gas, all right? So the question I'm going to ask is basically, what is the value of delta H for CO gas? I'm sorry. C solid plus half O2 gas to give CO gas. And what's the delta H value for that? All right. Now, based on the information provided before, the delta H value for going from carbon to carbon dioxide is minus 393.5. Minus 393.5 kilojoules, all right? And then for the reaction going from carbon monoxide to carbon dioxide, which is this right here, that is minus 283.0 kilojoules. So 283.0 kilojoules, all right? So based on these two equations and their values for the enthalpy changes, respectively, the question is, what is delta H equal to for the reaction going from carbon to carbon monoxide? So the way we're going to do this is that we're going to compare each of these equations to this one. And firstly, we notice that in this case, we have a carbon here, we have a carbon here. So I will leave this equation as it is, right? But in this case here, we have a carbon monoxide on the left side of the equation, but here we have it on the right side, right? Now, what I'm going to do, oh, by the way, this should be negative here, right? So what I'm going to do is flip this equation here, because the carbon monoxide is on the right side here. I want to get this carbon monoxide on the right side, which means I'm going to flip the equation, which means that as a result of flipping the equation, I'm going to end up with CO2 gas on the left side to form CO gas on the right side plus half O2 on the right side. And as a result of flipping that equation, if you remember, whenever the equation is flipped, the sign changes, right? So in this case here, delta H will be equal to positive 283.0 kilojoules, all right? So what we're going to do now is add this equation here to this equation, canceling out the common items on both sides, right? In this particular case, the common items will be the carbon dioxide. And also what will happen is that half a mole of oxygen here will take out half a mole of oxygen here, right? So this becomes 1/2. So therefore, when you add these two equations together, you're going to get C solid plus half O2 gas to give CO gas, which is the same equation as this equation right here, which means that the delta H value, which is what the question is asking for, would be the sum of these two, right? So basically it's minus 393.5 here. 393.5 minus plus 283.0. And according to my calculation, this works out to be equal to minus 110.5 kilojoules. And that's how that is done. All right. Any questions about this? Any questions about this one? Now, this one is a rather simpler, one of the more simple type examples of a Hess's law question. I'm going to show you a more complex one, but the idea is still the same. But in the next one, there'll be more maneuvering, for lack of a better word, that will be involved. All right. Okay, so there's no question about this. Let's move on now to the more complex example, which is this one. In fact, I'm gonna need a space, so let me copy and paste it onto the Word document. Okay, so okay, so here is the question. It says calculate the enthalpy change for this reaction, right? 2 carbon reacting with 2 hydrogen to form C2H4, right? And it gives you these 3 equations and their corresponding delta H values, all right? So we're gonna do something similar. We're gonna take a similar approach to what we did in this simple example just a while ago. In that, we're gonna compare each of these equations to what we have here, right? And the first thing I notice here, comparing this equation to this equation, we notice that we have a carbon here, but we have 2 carbons here, right? So, and the carbons are on the same side of the equation. So what I would do to this equation here is that I would multiply by 2 because I want a coefficient of 2 here, but that means I have to multiply the entire equation by 2. When I do that, I'm going to end up with 2 carbon solid plus 2 O2 gas to give 2 CO2 gas, and as a result, I have to multiply that by 2 as well. So delta H for this equation would be 2 times minus 393.5 kilojoules. All right. In fact, let me work that out right now. So 393.5 minus times 2. So that gives minus 787.0 kilojoules. All right. Okay. Then I compare this equation C to the first one. And what do I notice? I notice that C2H4 is on the left side here, and it's on the right side here. So what that means is that I have to flip this, right? And if I flip it, I'm going to end up with 2 CO2 gas plus 2 H2O liquid to give C2H4 gas plus 3 O2. Now, my question to you is, what's going to happen to the delta H value for that equation as a result of flipping? That's the delta H before flipping. What's going to happen to the delta H after flipping? Sign. The sign is going to change, right? So that will change from minus 1410.92 plus 1410.9 kilojoules, all right? Okay, so now we get to equation D. Again, we're going to compare this to the first equation, and the first thing I notice is you have 1 hydrogen here, and you have 2 here, right? So what I would do with this equation is that I'll multiply that by 2. So if I multiply that by 2, I'm going to end up with 2 H2 gas plus 2 times half, which will be 1 O2 gas. And then on the right side, 2 H2O liquid. So what does that mean for the delta H value for this equation? How do we get this? This is the delta H before we double everything on this equation. So what does that mean for this? What will be the delta H value for the equation after doubling everything? What's going to happen to this value after doubling everything? Well, how about you guys out there in Zoom? What did we do for the first equation? Because we doubled the first equation as well.
We multiplied it by 2.
Exactly. So this will become 2 times minus 285.8 kilojoules. So let me see what I get. 285.8 negative times 2. So according to my calculation, this works out to be equal to minus 571.6 kilojoules. All right. So the next step, if you remember from the previous example, what we did is that we add everything, right? And again, you need to remember when you're adding, you cancel out those items that are common to both sides. So based on what we see here, what will cancel out? What will cancel? Who? No. You have 2 hydrogens here, but you have no hydrogens on this side. Right, so that will remain. So what will cancel out, folks? Yes, ma'am. The water, okay, the 2 water molecules here and here. Anything else?
The oxygen.
Okay, yeah, you're right, because you have 2 plus 1, 3, which cancels out with the 3 oxygens there, right? Anything else? What else will cancel out?
CO2.
Exactly, the CO2s will cancel out there and there, right? So there's nothing else to cancel, so you'll be left with carbon solid plus 2H2 gas on the left side of the equation, and then on the right side of the equation, you're gonna have C2H4 gas. And again, this will be the same as the equation that you're trying to find the delta H value of. So to get the delta H value of this, right here to avoid confusion, the delta H value for this reaction will be the sum of this plus this plus this, right? So that will be minus 571.6 plus 1410.9 minus 787.0. And the answer you'd have to round off to 1 decimal place. So the answer I got, and please correct me if I'm wrong, I got 52.3 kilojoules as the final answer. Right? Okay, any questions about this one? Any questions? Any questions? Okay, so let me go to the assignment because there's some, like this question right here, very similar, right? In fact, hold on, let me check on. Okay, so number 9, we're going to start with number 9 here. It says calculate the delta H of the reaction, and it gives you the balance equation here. From the following data, it gives you each of these equations and their corresponding delta H value, right? So I want to hear what you guys would do based on what we have just done in the previous example, right? So, what's your first step? Okay, so what's the first step? Feel free to look at your previous example to help you with this. Let's start with the ammonia. Right? We have 4 ammonias here, right, on the left. And we have 2 ammonias here on the right. So what would you do to this equation in order for you to get 4 ammonia on the left? And let me give you a hint. You need to do 2 things.
One of them be flipping.
Correct? You have to flip it. And what's the other one? I'm sorry?
LPG.
Changing? Well, okay, you're right about that. I wasn't thinking about that, but he's right. The sign will change because you flip it. But there's one other thing I'm looking for in terms of what we'll do when you to get the 4 ammonia on the left from the 2 ammonia on the right. One is flip it and the other is what?
Multiply the equation by 2.
Exactly. So let me just put here that you're going to flip and multiply by 2. All right. So when you flip this equation and multiply by 2, you're going to end up with 4 NH3 gas on the left to form 2 N2 gas on the right plus 6 H2 gas on the right. And as he correctly said, you're going to change the sign of this. But not only that, you have to do what? So you have to change the sign of this. So that becomes 91.8. But there's something you need to do to this as well.
Multiply by 2.
Multiply by 2, exactly. Because you doubled the equation. So let's see what that gives. 2 times 91.8. So according to my calculation, this works out to be equal to 183. In fact, 184. You have to round off the 3 things. So 184 kilojoules. All right. Okay, very good. What next?
Multiply the third equation by 3.
Multiply which one? This one?
Yeah, by 3.
By 3. And the rationale for that is because you have 6 water molecules here and you have 2 here, right?
Yeah.
Okay, so we're going to multiply that by 3. You're going to end up with 6 H2 gas plus 3 O2 gas to give 6 H2O gas. So what happens to the delta H? Let me draw a line here. What happens to the delta H for this one? Multiply this value here by 3, right? So that's minus 483.6 kilojoules. And let me see what that gives. That gives 483.6 minus times 3. So we have to round this off to 465. So that will be minus 1451 kilojoules. All right. Okay. What next?
Multiply the first one by 2.
Multiply the first one by 2, and that's because you have 4 NO here, and you have 2 here. NO is on the right, so we don't need to flip it. So you're correct. Who said that? I'd like to give credit to.
It was Luke Wheeler.
Oh, okay, good. All right. So the result would be 2 N2 gas plus 2 O2 gas to give 4 NO gas. And of course, delta H for that reaction will be double of what it was before, which will be 2 times minus 180.5 kilojoules. And then let's see what that gives. So 180.5 negative times 2. So according to my calculation, that would be minus 361.0 kilojoules, all right? And then, so here we multiply by 2, okay. So, what next? Yes, ma'am.
Would it be possible 361? Oh, no, sorry, no, you're right, I forgot, sorry.
We didn't flip it, right?
Sorry.
Okay, what next?
And
Add them up, okay, so that means that we have to look at what will cancel out, right? So I want you to tell me what, if anything, will cancel out.
6 hydrogens on either side.
Okay, very good. What else? See if I can scroll.
The 2 nitrogens. Wait,
I'm sorry?
he said the 6 hydrogen.
Oh, he said, I thought he said the nitrogens. Okay, but yeah, the hydrogens will cancel as well, yeah. All right, and I think that's it. There's nothing else left to be canceled, so we simply add what's left, which would be 4 NH3. And in this case, please notice, very common error that's still sent to me. If you have the same substance on the same side, you add them. They won't cancel, right? So in this case, it's 2 plus 3. So that's 5 O2 gas. This is the gas. And then on the right side, you're gonna have 6 H2O gas plus 4 NO gas. So that means that the delta H value that we're going to calculate here would be the sum of this, and this, right? So that would be 184 minus 1451 minus 361.0. And according to my calculation, this works out to be equal to minus 1628 kilojoules. So this is the answer right here. All right. Okay, any questions about this one? Any questions? Any questions? No questions? All righty. Moving along. Whoops. Okay, I take it I can clear this, right? So clear this. And let me scroll down. Let's see what's. Okay, so number 10, very similar. I'm gonna leave you to do that one on your own, right? But basically, if you understood what we just did, you should be able to do number 10. Excuse me. Let me scroll down here and see what's it. And number 11, right? So I'm gonna leave number 10 and number 11 for you to do on your own. If you have any problems while doing these problems, please feel free to come and see me or call me, or we can link up on Zoom. All right, so let me go back to the PowerPoint here and try to finish up this chapter. Now, oops. Okay, now, the thing about enthalpies is that they can be affected by, several factors. Can be affected by temperature, can be affected by pressure, and other things, amount of substances involved and so on, right? Now, if you want to make meaningful comparisons between reactions in terms of the enthalpy changes, then we have to take into account that, well, firstly, let me just say this. Any change in enthalpy of any reaction, by definition, would be basically the sum of the enthalpy of the products minus those of the reactants. Problem is that you cannot measure those directly, right? You cannot, it's impossible to measure directly the enthalpy of products, any substance or reactant, right? Even though by definition, that's the way that you calculate delta H. So what was decided upon by the powers that be is that we end up standard conditions for making such comparisons. And basically, see here. Based on that, we have what is what we call a relative scale, right? Now, the standard conditions that have been adopted by whoever that everybody has to follow are: 1, the pressure of any gases must be at 1 atmosphere, and the temperature of all the substances must be 25 degrees Celsius, right? Those are the standard conditions. Please do not confuse these standard conditions with SDP, right? SDP, standard temperature and pressure, that has to do with gases, right? We learned about that in the previous chapter. In this case, we're talking about all reactions and the standard condition, right? So basically, all the enthalpy changes that we're going to talk about is under standard conditions when it comes to making these kind of comparisons. So at this juncture, I want to define two terms, one of which is the standard enthalpy change, right? And this is a symbol here, delta H, and then there's a small O or zero, which is a superscript to the right, all right? So basically, whenever you see this symbol right here, the O, that means standard conditions. Temperature is 25 degrees Celsius, and the pressure is 1 atmosphere if there are any gases involved, right? So please remember that this is dealing with standard conditions. Now, there's another term which is related to this, which I need to introduce to you as well, and that is called the standard enthalpy of formation, right? That is basically, by definition, the standard enthalpy change when you have 1 mole of a substance being formed from its elements under standard conditions. Again, standard temperature being 25 degrees and standard pressure being 1 atmosphere, all right? Now, to illustrate what we mean by standard enthalpy of formation, I'm going to use this example right here. Let's say you want to find out what the standard enthalpy of formation of methanol is. Methanol is CH3OH, right? Basically, what you'd have to do, if possible, is have a reaction between all the elements in their standard state that makes up that compound. In other words, you have to have carbon, hydrogen, and oxygen reacting to form methanol, right? However, the equation for the reaction must be set up such that the coefficient for the methanol is 1, right? Now, the consequence of that is that for other substances, you might end up with fractional coefficients, such as right here, right? In any case, basically, when we're talking about the enthalpy of formation of methanol, we're talking about the enthalpy change where all these elements react to form 1 mole of methanol. And that was determined to be equal to minus 238.7 kilojoules, all right? So basically, and this is under standard conditions, as I said before, 1 atmosphere for all the gases involved and the temperature being 25 degrees Celsius, all right? So basically, data like this have been collected. In fact, let me just show you the table that you'll have access to, which gives you such values. So let me go to Canvas here, go to files, and then go to tables. No, not that one, sorry. This one, no, this one, thermodynamic data, that's the table that you will have access to for your next test. And I'm going to show you what to use. Okay, so this table gives you a list, a very comprehensive list of different substances and their enthalpy of formation, right? Remember, the enthalpy of formation is the enthalpy change for the formation of 1 mole of the substance, right? For now, you won't be paying attention to this column or this column, right? For those of you who have to do Chem 2, you're going to learn about these two values, the free energy and the entropy. But at this level, you don't need to worry about that. You only need to worry about this first column here after the column for the substance, right? So basically, just to give you some examples, let's say we're dealing with aluminum oxide, right? This here is a value, minus 1,675.7 kilojoules per mole is the enthalpy change required or that will occur when 1 mole of aluminum oxide solid is formed, right? Another thing I want to point out is that you have to pay attention to the state, whether or not it's a solid, liquid, or gas, because it actually depends on that. Let me give you or show you the example of bromine. In the case of bromine liquid, right, its enthalpy of formation is 0, but in the case of bromine gas, its enthalpy of formation is 30.91. So the actual state matters, right? So whenever you're using these values, pay attention in the question, pay attention to the state of the substance, right? Now, There's a very important question being asked. Let me go back to the PowerPoint here. The question being asked here at the very bottom of this page is, what is the enthalpy change of formation for an element in its standard state, such as oxygen, such as any other element that exists in nature, right? The question is asking, what is the enthalpy of formation of such elements? Well, if you think back to the definition of the standard enthalpy of formation, right here, it is an enthalpy of formation for one mole of a substance from its element, right? So if you're dealing with oxygen, right? To form oxygen, same state, then the enthalpy of formation of oxygen is what? What do you think?
0.
0, exactly. And that is true for all elements that exist under standard conditions. So if you go back to the table right here, if you go back to the table, if you look at it carefully, you see that for all the elements, you start with aluminum, and then scrolling down to arsenic, right? All of these have a value of 0, right? So elements that exist under normal, or let me not say normal, under standard conditions, their enthalpy of formation is 0. That's true for boron. That's true for bromine liquid, right? That's 0. Remember now, bromine gas is 30.91, right? But bromine liquid is 0, and calcium is 0. So all the elements, right? You're going to see that consistently down the table. All elements will have an enthalpy of formation of 0. All right. Now, back to PowerPoint. Okay, so how do we use these values to calculate the enthalpy of a reaction? It's actually very simple, even though it might be a bit cumbersome in terms of doing the actual calculation. Basically, we use this equation right here. The enthalpy of the reaction will be equal to this minus this. Now, you might be wondering what all this means, right? This part here represents the sum of the enthalpy of the products, right? So basically, on the reactant, on the right side of the equation, you're going to add up all the enthalpy of formation of products, and you're going to subtract from that the sum of the enthalpy of the reactants, right? Now, delta HF products basically means the enthalpy of products, and this symbol here basically represents the coefficient of that substance that is in the balance equation, right? And then you just work out the difference between the two, and that will give you the enthalpy of the reaction. Now, you could use Hess's law, but that's a bit more cumbersome and complicated. So it's far easier if you have the values of the enthalpy of formation, which you will have because of the table. Then basically all you have to do is use this equation here to determine the enthalpy of the reaction based on the enthalpy of formation on the standard condition. All right. And I think the next slide is an example of this. Whoops, sorry. So let me copy here. And let me oops. Okay, so this question, it gives you the balance equation, and the question is asking for you to use the values from the table that I just showed you to determine delta H, right? So basically, as I said before, to calculate delta H, that will be equal to the sum of the enthalpy of the products minus the sum of the enthalpy of the reactants, right? So what we have to do is write down an expression. We have to multiply its value by the coefficient. So that will be 4 times the enthalpy of formation standard of carbon monoxide, right? And then we're going to add to that the enthalpy of formation of hydrogen. But guess what? Hydrogen is an element, right? And as we said before, all elements will have an enthalpy of formation of 0. So we don't need to even look up that. We can just put 0 right here, right? And then I'm going to put that in square parentheses. And then I'm going to now look at the expressions for the other substances on the left side, starting with methane, CH4. So that will be 3 times the enthalpy of formation of methane. CH4. And then I'm going to add to that 2 times the enthalpy of formation, enthalpy of formation of water. And again, I can't emphasize this enough. Make sure you pay attention to the states, right? Because like water in the liquid state will have a different value compared to the gaseous state, right? So that's why I'm very specific and particular about including the states when I'm writing these down, right? And then now we get to carbon dioxide plus the enthalpy of formation standard for carbon monoxide gas, right? And then I'm going to put that in square parentheses. This should be gas here as well, all right? So what we have to do now is look up the values. And I'm going to need you guys out. If you guys can bring up on your devices the table I just showed you, which is this table right here, right? Because I need you to look into it and let me know what these values are. So if you can bring that up on your devices, I'd appreciate it. So let's start off with this side. 4 times the enthalpy of formation of carbon monoxide. So can somebody tell me what the enthalpy of formation of carbon monoxide gas is? Yes, ma'am.
Negative 110.53.
Minus 110.53. Okay. And that would be kilojoules per mole, right? Okay. And then now, so that takes care of this side. And then now on the right side, we're going to have 3 times the enthalpy of formation of methane. Oh, by the way, I just remember something. Going back to the table, right? For organic compounds, they have a separate section in this table. It's I think on the last page. Right here, right? So methane is right here, CH4. And here is the enthalpy of formation of methane, minus 74.81. So I need to write that down. Minus 74.81 kilojoules per mole, all right? And then now, 2 times the enthalpy of formation of H2O liquid. I keep rewriting that crap. Okay. Okay, 2 times the enthalpy of formation of H2O liquid. So again, can you help me out here? What's the enthalpy of formation of H2O liquid? Not gas, but liquid.
Negative 285.83.
Minus 285.
0.83.
3. Okay, thank you very much. And then the last one is the enthalpy of formation of carbon dioxide. I forgot to put the 2 here. That should be carbon dioxide. What's the enthalpy of formation of carbon dioxide gas? Well,
Negative 393.51.
okay, I'll take your word for it. Kilojoules per mole. All right. So let's work out the different parts. So 110.53 minus times 4. So according to my calculation, I'll be minus 442.12 kilojoules. And then I'm going to subtract from that 3 times 74.81 minus. So this I have to round out to 4 sig figs. So I got minus 224.4 kilojoules plus, and then 285.83 minus times 2. Okay, so, and again, folks, please correct me if I'm wrong. Do these calculations with me so as to keep me on the straight and narrow. But I got for this one, minus 571.66 kilojoules. And then, I'm going to minus 393.51 kilojoules per mole. Mole per mole and per mole. All right, and then now I'm gonna do the final calculation. So, okay, so 224.4 minus 571.66 minus 393.51. And then I'm going to put a minus sign in front of that, and then I'm going to subtract from that 442.12. And the answer I got, now, let me see. I need to round this off to 1 decimal place. So the answer I got will be 747.5 kilojoules per mole. And that's the final answer for this problem. Right? Okay, any questions about this one? Any questions? 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 Okay, we go back to the PowerPoint. Now, the next question here is very similar. Only difference in this case is that whereas they gave you delta H here, or I'm sorry, they did not give you delta H here, but they gave you delta H here. And what the question is asking for in this case is the standard enthalpy of formation of isopropyl alcohol, which is this compound right here. All right. So basically the approach will be the same, but what you're trying to find is the enthalpy of formation of this compound. All right. So I'm going to leave that for you to attempt as well. Again, if you have any problems doing this, then feel free to come and see me about it. All right. And that's basically the end of the chapter. Now, let me just say that, as far as the assignment is concerned, there is another link. Let me go here. So we're talking about assignment number 6. There's another link right here, which you need to attach to this link when you're submitting your assignment. And basically that link gives this document which has these questions. Again, it's asking for the same thing as we did before. You're going to use a table, the values in the table, to determine the standard enthalpy of these reactions right here. So it's the same thing. You look up the values, you add up the product values and subtract it from the total of the reactant values, and that's it, right? So that's what this page is all about, right? So what I'm going to do now is open up a Dropbox for this assignment. So this is assignment 6. Okay, 27. Let me go here. So that will be Monday. Okay, so that is that. All right. All right. That will be it for today. Giving you a little break. So I'll see you guys on Tuesday. I should have your test graded, but I keep consistently at it. You should see your grades in the system by Sunday. And I should be able to email it to you by Monday, your graded test, all right? So something for you to look for. Yeah, you do. Yeah, you too. Take care. Okay, and for you guys out there in Zoom, I'm signing off now.